Lecture 2.4, Energy Bar Diagrams and Examples. Why is the first law so important? To really answer this question, it's best to look back at mechanical energy. From your introductory mechanics course. And the way I'll do this here is that I'm going to give you an analogy. And in this analogy, what we're going to see here is that here's what we know. We know that mechanical energy is path independent. And only depends on the endpoint. In other words, if I'm going to go from state 1 to state 2, so how do I say this? Let me start with the picture first. So I'm going to imagine that I have a cart right here. And what I'm going to imagine here is that on this cart, I'm going to assume that this cart is going to have some initial speed here. And I'm going to have two different paths. So I'm going to imagine that this is the path of 1. And so when I get to this state here, how about if I label this state 1, and then the cart is going to go to state 2. And so when I look at this cart, and it gets here, we can see here is that the speed of this cart is going to be higher at point 2. Now, this path here, I'm going to call it path A. To show that this is path independent and it only depends on the endpoints, then I'm going to select a different path that maybe goes up like this here. And I'm going to say that this here is path B. So what mechanical energy is really telling us here is that the path taken between state 1 and state 2 does not matter. Only the endpoint. And the way we write this is we write this as conservation of total mechanical energy. So if I look at the mechanical energy at state 1, well, I could see here is that, I mean, we could, I don't know where we want to put our potential. I'm going to say that I'm going to set my potential here. My height here, I'm going to define this as 0 right there. So if I look at this thing, they have a high kinetic energy. Maybe, I'm going to be careful how I set my potential. I'm going to take that back. I'm going to leave it arbitrary. So what I'm seeing here is that at state 1, I have a high kinetic energy, and then the cart is going to have low kinetic energy. But what we mean by conservation of mechanical energy is that energy is being transformed into other forms and cannot be created or destroyed. So from a bar diagram viewpoint, I'm really saying something like this. So if I have this amount of, let's say, gravitational potential energy, and I have this amount of kinetic energy, what we know here is that as you move through the system, what you're going to find here is that the energies have to adjust themselves or rearrange themselves to keep what? E mechanical equal to a constant. So if all of a sudden I have this amount of potential energy, then we have no choice but to have this amount of kinetic energy. And all we know is that this total mechanical energy is a fixed quantity. It's a constant of the motion. And that's what we mean by work being done by a conservative force. So what this means here is that we really say this here. We say that the potential and kinetic energy terms are not conserved quantities, but E mechanical is. In other words, potential energy and kinetic energy must adjust themselves to keep E mechanical equal to a constant. In a little bit more detail, we could then say that potential energy is definitely path dependent. And the reason why it's path dependent, because when I compare the potential energy at state one, that is clearly not the same as the potential energy at state two. Therefore, it's not conserved. It's not a conserved quantity of the motion. I could say the exact same thing for kinetic energy, because when I look at the kinetic energies, we see that they're not the same. But what is the same is mechanical energy. Mechanical energy is path independent. And as a consequence, these energies must equal each other. And therefore, this is what we call a conserved quantity. Now, what I want to do here is that I want to apply these same ideas to the change in internal energy. So now what we're going to do here is that we're going to apply the same ideas to the change. Note, I didn't say internal energy. I said the change. So the change in internal energy. Which I, of course, we have been defining like this. So we're going to apply this, and what you're going to see here is that the change in internal energy plays a similar role to the mechanical energy. But what I need you to do here is that remember that we said here is that the internal energy for an ideal gas is going to be K micro, that this is proportional to the temperature change. That's an important piece right there. Okay, so this is an important piece to my discussion right now. Okay, so now why is this an important piece? Okay, so this is, remember, I'm going to take the same idea, right? This is important. We're saying that the change in internal energy is process. We've been talking about thermodynamic processes, but they also go by the name of a path. They're path independent. So the internal energy is process independent, it's path independent, and only depends on the endpoints. And in this case, it has to be proportional to the change in temperature. So what's crazy about this, I could say that stated differently, the change in internal energy does not care about its past history. And what I mean by past history, the process that got it to those states here, only on the endpoints. So I would say that this is a really important statement here, to at least get this conceptually. In fact, I think I'm going to do this. I want to make this stand out as strong as possible, right? Fluorescent red here. Now, to tell you what do I mean by this, look what I'm going to do here. I'm going to give you a conceptual point to really stress, stated differently, the change in internal energy does not care about its past history, only the endpoints. So when I say only the endpoints, I really care about the change in temperature. So here's what I mean by this. So think about a conceptual point here. So what I want to do here is that I'm going to heat a cup of water to 100 degrees Celsius. So one can use either a stove or a microwave oven. Now note, these are two different heating processes. So then so the stove, it uses the ideas of conduction, and this uses the idea of electromagnetic waves. Two very different processes. So the question is, does it matter how the water is heated? And the answer is absolutely no. It only depends on the endpoints. And in this case, maybe what we have here is that we have initial temperature, and let's call this 22 degrees C, and final temperature, which is equal to 100 degrees C. So when I look at the internal energy says that this thing is going to be proportional to the temperature change. So in this case, it's going to be 100 minus 22, which will then be 78 degrees Celsius. It didn't matter how I got there. It didn't matter how I got there. All I care about is the endpoints. So what I'm saying here is that now if I look at the internal energy, we're going to say here is that this thing is process independent, which is also K micro. And we know that this guy is going to be a constant. So what you're seeing here is that I have working and heating. And what we know about working and heating is that they are process dependent. But the combined, combined combination is process independent. And so the way I'm going to look at this is very similar to the example here. So if I start to look at this thing, I'm really saying this here. The workings and heatings must adjust themselves to keep the change in internal energy equal to a constant. And what I mean by adjust is that I'm saying that if I focus on two states and I look at the difference, the path does not matter. So then what am I going to have? Maybe the work goes high right here, and then it goes small, whereas the heat starts off small, and then it goes high. In other words, these guys have to adjust themselves to keep total change in internal energy a constant. So let's look at a diagram to give you a physical sense of this. So I'm going to now look at some example. And I'm going to look at this here. So what you're going to see here is that in, let's say, an ideal gas, undergoes a thermal process, maybe a series of processes that takes the gas from state 1 to state 2. So let's just pick some example here. So here I go. So I imagine that I have a PV diagram like this. And I'm going to pick my state right here. And this state is state 1. And then I want to go to this state, which I'm going to call state 2. So if I look at the pressures, we can see here is that the pressure of 1 is going to be here, and then the pressure of 2 is going to be right here. And then we see here is that this is the volume of 1, and this is the volume of 2, where I'm looking like this here. So now all I care about is getting from state 1 to state 2. So I could imagine that I take a path that goes like this. This I'm going to call path A. Now, let's say that I take a path that goes in this direction. I'm going to call that B. So what I'm seeing in path A, or processes A, I'm seeing here that I'm going to have isochoric cooling followed by isobaric heating. And if I look at path B is just the opposite. I'm going to have isobaric heating followed by isochoric cooling. So what do I know about these guys? We know here that when I look at, so by definition, we know that the thermal work is the negative of the area. So calculating the workings, here's what we're going to see here. Well, let me copy this guy just to be fast. So I'm going to copy this, and then I'm going to paste this guy right in here. So I don't care about B. Let's just focus on A. I'm going to calculate the work of A. So what I'm seeing here is that the work is the area. So this guy, this area is essentially the work of A. So if I was to calculate that work, I'm going to see that the work of A, you could see it's just the area of the rectangle. So it's got to be minus P2 times the difference in the volumes. And that negative sign is there because thermodynamic work is the negative of the area. Now let's go look at work or path B. So in this case, we have here. So when I look at this, you can clearly see that this has a larger area. So then the magnitude of this work has to be larger. So when I go and I calculate this work, here's my negative sign. You're going to see that I'm going to have P2, oops, not P2, P1, times the volume here. And what you're seeing here is that we see that the work of A is greater than the work of B. Now, why is that? This is less negative. This is more negative. So now if I start to put this all together, what am I seeing here now? What I'm seeing here is that because the change in internal energy is path independent, that tells me here is that the change in the internal energy, whether I go along path A or whether I go along path B, it does not matter. It is a constant. It's path independent. But what you're seeing here is that the heatings and workings have to adjust themselves. So what do I mean by that? So then we're going to say here, the workings and heatings must adjust. Okay, I want to put that big. Must adjust themselves to keep delta internal equal to a constant. So look at the areas. Look what happens here. So if I have, in other words, so if I have a small area versus a big area, then that means that then the heatings have to be different in order to keep them fixed, keep that quantity fixed. So in summary, we could then apply the same idea that we did before. Workings are path dependent. And the reason why they're path dependent, because when I look at the workings, they are not the same. So we then say that this is not conserved. It's not a conserved quantity of nature. I can say the exact same thing with heating. Heating is path dependent, and the reason why is because you can see here that these guys are not the same along the different paths. We can say that the change in internal energy is path independent. And the reason why is because I now look at the internal energy of A versus the internal energy along path B, and they're exactly the same. So therefore, it is a conserved quantity of nature. And as I already said here, the workings and heatings must adjust themselves to keep the internal energy constant. Now, this lecture is followed by examples 2.1 and 2.2. These are extremely important. They set the framework for all problem sets, quizzes, and exam 1. Pay close attention to those examples. And if you have questions, come and see me.